Hello students, in the previous sessions we discussed upon the railway topics related to the railway track components. So we discussed on what is the requirement of various components and what are the various types available and how that has to be designed. All those aspects will be studied in the first part of the module 1. So in the second part of the module 1 we have the topics related to the railway alignments. And in this session, we will be discussing in details about the types of railway gradients and what is the limitations for providing the railway gradients will be discussed in details. So to start with that, first we will understand what is a railway alignment. So we all know that marking the center line of the railway, that we will call it as the alignments, or you can also call alignment as a line which refers the direction and position that is given to the center line of the railway track on the ground. So that can be in the horizontal or in the vertical planes. So mainly the alignment, it includes the two alignments, in that the first we will have the horizontal alignment and the second one is the vertical alignment. In the horizontal alignments, it will gives you the direction of the railway track in the plane. So that will include what's the straight part and also the curve it follows. Whereas in the vertical alignment, it will shows the direction of how the railway will run in with respect to the vertical plane, so which includes the level track, the gradients that is provided, and also the vertical curves. And now, what is the need for the construction of the new railway line? Do we really require it? So we have some of the reason why it is required for us to go for the construction of the railway track. The very first reason is for the strategic reason. So we may have to, during the emergencies, military emergency, it may require for us to move the military movement, for maybe to move the persons or even the military equipment from the one place to the other place. So for that such kind of military emergency, it may require for us to extend the existing railway track to the new point of strategic importance. And the second reason is the railway tracks will be considered for keeping in view of certain political importance that will be considered. And also we all know that the providing the transportation facilities and development of any region is closely related, and the experience has shown that once the railway network is constructed in the backward area, it is found that it will develop in a very faster rate. So if you want to develop any region, provide a good transportation facility, that you can see the development in the faster rate. And also it may require for you to connect between the two new trade center, so where maybe in some of the places where the industries might have established, so we have to quickly transport the goods between such trade center. So if you want to connect any new trade center which has been developed very recently, you can go for the construction of the new railway network. And also it may also be constructed to shorten the existing railway link, so to connect between point A and B. So if the existing line is too far, so we may think of the connecting with the new railway track, which will reduces the distance traveled between the 2 points A and B. So these are some of the reasons why we may have to go for the construction of the new railway network. And the next, as we told, we'll be discussing about all the geometric components in the design of the tracks. And what is the necessity? So first necessity is we all know railway track need to be properly designed, similar to the highways, because always improper geometrics that leads to the various disadvantages. Maybe the cost of construction will increase very much, the improper gradients, and also it may lead to some of the accidents can occur because of the improper gradients that has been provided. And construction of the new track, it will require a huge amount of investment, and if because of the improper geometrics, it may feel very difficult to upgrade the existing condition, and also the budget requirements would be very high, and the cost of construction to realign any network will be very difficult. So to avoid all these things, we have to go for the consider the all the geometrics need to be properly considered, and which is required to ensure the smooth and safe running of the train, and also with the help of the proper geometrics a maximum speed can be achieved, and the trains will be capable of carrying the heavy axle load, and the track which has been constructed considering all the geometric aspects will be safe, and the number of accidents and the derailment issues because of the defective permanent way can be avoided. And also the well designed track is the one which is having a less maintenance, and also the geometric has to be taken in such a way that for good aesthetics will be provided. The first geometric components what we will be studying with respect to the railway alignment is the gradients. So first the gradients are provided to negotiate rise and fall in the level track. So your track will be running like this. If a level changes, either that can go in the upward direction or that may go in the downward direction. This change in level we call it as the gradients. And if your gradients goes in the upward direction, we call that as the rising gradient or the positive gradient, and if the level goes in the downward direction, we call that as the falling gradient or down gradient, so usually represented with the sign negative sign. Okay, so for example, the gradients would be usually represented in terms of 1 in n, or it can also be represented in terms of percentage. For example, for every 400 meter, I am rising my gradient for an amount of 1 meter. For every 400 meters in the horizontal direction, your rise and gradient in the vertical level is 1 meter. So now the gradient will be expressed as 1 in 400. Or that can also be expressed in terms of percentage. So when you take the percentage, your vertical is 1, horizontal is 400 divided by 100. That is equal to 0.25%. So hence the grades can be represented either in terms of 1 in n or in terms of percentage. Now first we'll discuss on the what are the objectives of providing the gradients. So now the gradients has to be provided sometimes to reach the various station at a different elevation, and we may have to follow the natural contours of the ground to an extent that is possible. So always to avoid the earthwork that is cutting and filling that is required in the construction of the railway track. So to follow that natural contours, we may have to go for the providing the gradients, and to reach the different station at the various elevation, and also the last to reduce the cost of earthwork required. So once the natural contours are made, it will obviously reduce the amount of earthwork done, and which will in turn reduces the cost of construction of the railway track. And now the various types of gradients that is provided in the railways that can be taken under the considered in the 4 headings. The first one is the ruling gradient, second pusher or helper gradient, momentum gradient, and gradients in the station ad. So we will discuss on what all these gradients, when it will be provided, and what are the limitations. So here first we'll talk about the ruling gradient. As the name indicates, ruling gradient is nothing but the maximum gradients that can exist in the any section of the track. So why it is required? So usually the load, how much the load carried by the train, that depends upon the first thing is the gradient, and second is the power of the locomotive. So now depending upon what power is available, you can power of the trains that will run on that particular section. So now we can calculate what should be the gradients that is required to haul particular load value. So we will be knowing what is the load carried by the train, and the power of the engine power of the train is also fixed. So now considering these two, we can fix up the what should be the gradients that can be provided in that particular section. But the gradient what we calculated depending upon these two conditions, that should be below the ruling gradient. So your gradients must never increase more than the ruling gradients. So because that will determines, and also the ruling determines the maximum load that can be hauled by the locomotive. So now what is the limitation? So in the plain terrain, it is all these delimitation what I am giving you as per the IR standards, which is recommended by the code. So for the ruling gradient in plain terrain, that should be in between 1 in 150 to 1 in 250. I'll repeat again, 1 in 150 means for every 150 meter horizontal distance, a rise should be equal to 1 meter. This is how the slope has to be provided. And the same thing in the hilly region, the slope value is restricted, the gradient value is restricted to 1 in 100 to 1 in 150. So once the ruling gradient has been specified for a particular section, so all other gradients what you have provided, that should be flatter than the ruling gradient what is just considered. The second gradient what we have is the momentum gradient. So momentum gradients are usually steeper than the ruling gradient, and the momentum gradient will be overcome by the train because of the moment it gathers while running on the section. So how it will be provided? Usually when the momentum gradient is provided, it will always follow the downward gradient followed by the upward gradients. So in this situation, when the train comes down in the falling gradient, it would acquires good speed and momentum, so which will gives the additional kinetic energy to the train, and which will helps to move in the upward gradient. So what momentum that is acquired during the coming down of the hill, that will be used to overcome the positive gradient or the upward gradient. Okay, so in this section where usually when such gradients are provided, there should not be any obstacle in the form, especially in the form of signals, which may bring train to the critical conditions. The next gradient we have is the pusher or helper gradients. So in the hilly region, especially this will be provided in the hilly region, where the rate of rise of terrain becomes very important when trying to reduce the length of the track, and sometimes we may have to take the gradient deeper than the ruling gradient. So now this all the ruling gradient especially provided to reduce the overall cost of construction. So in such situation where your gradients are very steep compared to the ruling gradient, one locomotive may not be sufficient to haul your complete train. The entire load cannot be hauled. So to move your train in such condition, an additional locomotive or engine is required. So for example here, for our ruling gradient, I am talking about 1 in 150. So sometimes it is unavoidable for us to provide the steeper gradient. Maybe we will go for the construction of 1 in, so you can see here the limitation for the pusher gradient is 1 in 75. So that means that the steeper gradients are there. So now here, to climb this gradients, one locomotive may not be sufficient. So now we will use the additional locomotive, that we call it as the pusher gradient. So we will use another pusher at the back, so that will push your train forward. Okay, so when such type of gradient is provided, that we call it as the pusher or helper gradient. So usually the values varies in between 1 in 75 to 1 in 100. With additional one engine is generally used. And the last type of gradients we have is the gradients at the station yard. What should be the gradients that is maintained at the station yard? So usually generally the gradient what is provided in the station yard will be as flat as possible. And why it should be flat? There are two conditions why we have to make the gradient flat. The first one is if the gradients are negative gradients is there, if the slopes are provided, there are chances that these standing vehicles may roll and move away from the yard due to the combined effect of the gravity and the strong winds. And secondly, if any gradients are there in the station yard, to start the engine and to move train further, an additional energy is required for the locomotive, so that may leads to the additional fuel consumption. So to reduce these two, the movement of rail trains moving away from the yard, and also to avoid the unnecessary waste of energy while starting the engine, so we have to keep the gradients at the station yard as flat as possible. And maximum prescribed gradient at the station yard in the railway station is 1 in 400. Preferably whenever it is possible, you need to go for providing the slope as one gradient as 1 in 1000. If it is not at all possible to provide this gradient, you may go to provide the gradient up to 1 in 400 can be provided at the station yards. So next one we have the something called the grade compensation. So especially the grade compensation will comes into picture on the curves. So whenever the ruling gradient as well as the change in direction both exist, so the resistance of the track will be increased on this curve, because one thing is the gradient is provided, along with the gradient we have the curves also. During the curves also, the centrifugal force will be developed. So counteract that centrifugal force, we require additional energy is required. And also if you have the grades also, that may leads to the additional resistance to the movement of the train. So now what we have to do is to avoid, to reduce the resistance caused to the movement of the train, especially at the curve. So though the ruling gradient is prescribed, so sometimes we will limits the gradient what it has been provided. So the gradient what we provided will be still steeper than the ruling gradient what it is prescribed. So you can see here in the picture it is given, you can see, so this is the actually the how much gradients that need to be provided from we'll take point A, B, C. So from B to C, that is what the gradients need to be provided. But at the curve, since the resistance will increase because of the combination of the both gradients and the curves, the radius of the curve which has been provided, the gradients will be slightly reduced. So we make the gradient little steeper. So now what is the amount at which the gradient has been reduced? That we call it as the grade compensation. So from B to C, that's the ruling gradient or the maximum gradient what is to be provided, and I'll take this point D. So but this is the gradient from B to D is the actual gradient what it is provided at the curve. So because to reduce the resistance that is caused for the movement of the train at the curves. So now what is the amount at which the grade has been reduced? That we will call it as the grade compensation. So how much that need to be compensated? So that depends upon the type of the track, and it is given as for the BG track, we need to reduce the gradient by an amount of 0.04 percentage for every degree of the curve. Okay, the radius of curve may be 2 degree, 3 degree, 4 degree, 6 degree, it can be anything. But so the grade compensation what is given by the standards is for every 1 degree of the curve, how much that need to be reduced. So similarly for meter gauge track, the grade compensation should be 0.0 percentage per degree of the curve, and for the narrow gauge track, the gradient has to be decreased by an amount of 0.02 percentage per degree of the curve. So we'll take up one example on this grade compensation, and we'll look how the actual gradient will be provided on the. For the broad gauge, if you have a broad gauge track, the grade need to be compensated by an amount of 0.04 percentage per degree of the curve. So here the example here, this says that the ruling gradient is 1 in 150 on a particular section of broad gauge track. At the same time, we have a curve of 4 degree which is situated on the ruling gradient. what should be the allowable gradient. So now they are given, we have the value of ruling gradient is given as 1 in 150 is given for you. But they say that there is also a curve of 4 degree. So now whenever there is a combination of gradient as well as the curve, we have to slightly reduce the gradient what it is provided. So that is the grade compensation. And now they are asking to calculate what is the actual gradient that is provided. So first write down the data that is given for you. Ruling gradient is 1 in 150 and given it as a broad gauge track. So now for the broad gauge track, what is the grade? So consider that as per for the broad gauge track, so it need to be compensated by an amount of 0.04 degree percentage per degree. So now for us we have the radius of degree as 4%. So 4 into the prescribed grade composition. So here the actual what it is, the gradients what we have, that need to be reduced by the 0.16%. So the ruling gradient is given as 1 in 150, convert that into the percentage, because now the grade compensation we have it in terms of percentage. So first the gradient is given in terms of 1 in n, convert that into the percentage first. Vertical divided by horizontal multiplied by 100. So how do you convert vertical in divided by horizontal into 100? So that will convert your grade in terms which is there in the 1 in n to the x percentage. So now the percentage gradients what has to be provided is 6.65%. So now this 0.65% need to be reduced by an amount of 0.16%. That's a grade compensation. So actual gradient what has to be provided will be equal to the total gradient 0.65 minus the grade compensation, that is 0.16. So actually we have to provide a gradient of 0.151%. So or this is expressed in terms of percentage, convert that in terms of 1 in n. So how do you convert 0.51 divided by 100? So you can convert here 1 divided by 100 divided by 0.15. So that will give 1 in 196 is the actual gradient which is provided at that particular point where the combination of grade and the curve exists. So you can see here actually the ruling gradient is given as 1 in 150, but we are providing still the steeper gradient to overcome the resistance that is caused because of the combination of the gradient and the curve. So you take up another similar example. Here we have a broad gauge, the same thing, the actual ruling gradient need to be provided. So the information what they have given, the ruling gradient is given as 1 in 200 on a broad gauge track. Once again the curve, the degree of curve is 3 degrees superimposed on the above track. So the grade compensation is, what is the grade compensation for broad gauge track? At 0.04% per degree of drag. So now we have 3 degree curve which is situated on that gradient. So 3 into 0.4 will get around 0.12%. So the ruling gradient what they given is 1 in 200, convert that to percentage. How do you convert? Horizontal divided by vertical multiplied by 100. So we will get 0.5%. So this is the total gradient, the ruling gradients that is provided and the grade compensation. Okay. So now the actual gradient will be ruling gradient minus the grade compensation. So that will gives you the actual gradient to be provided, 0.38%. Converting that into the 1 in n type, so we will get the gradient to be provided as 1 in 264. So this is how you can calculate what should be the actual gradients that is required to be provided when you have the combination of both the gradients as well as the curve at any location of the track section. The next geometric components what we need to consider is the speed of the train. So what is the speed of the train achieved depends upon the strength of the track as well as the power of the locomotives that has been adopted in pulling the train. So and also if you use a diesel traction and the electric traction, higher speed of the trains can be achieved. And anyways, with the modernization of the Indian railways and the construction practice and use of electric traction, we can achieve the speed up to 150 kilometer per hour in the BG track, and in the meter gauge track the speed can be achieved up to 100 kmph. So these speeds are in the straight track. Okay, so what is the speed, and also when it comes to the curves, this what is the speed of the train achieved, that depends upon the what is the gauge adopted at the curve and the radius of the curve, rate of super elevation is provided, and the presence and the absence of the transition curve. So next, how to determine the speed of the train at the curve. So to determine the speed of the curve, we make use of Martin's formulas. As I already mentioned, the speed on the curves depends upon the various parameters, which includes the speed and the rate of super elevation provided and the gauge of the track. So now in the Martin's formula, we will get the speed relationship between the speed and the radius of curve will be given. And for considering the radius of the curve, what should be the speed achieved by the trains? That is given by the Martin's formula, and the speed also calculated considering the rate of super elevation provided and the presence or absence of the length of transition curves that has been provided at the curve. The speed is calculated depending upon the various consideration, and whichever comes minimum, that speed will be adopted by the trains. So now we'll look into that how the speed can be calculated with the help of the Martin's formula. So to determine that, we have three conditions. The first condition where the transition curve exists, the second curve where the transition curves are absent, and generally for the higher speed. The first two conditions will gives you the relationship between the speed and the radius of curve up to a speed of for the lower speed. So first thing is, when the transition curve is absent, and the speed can be calculated in the BG and meter gauge track as V is equal to 4.44 square root of R minus 70, or you can calculate this as 4.35 square root of R minus 67. So similarly for narrow gauge track, the speed can be determined with the second equation B. Okay, and these equations are valid, the relationship are valid only up to a speed of 50 kmph. If this train speed exceeds more than this, we cannot use this formulas. And similarly, if the transition curves are absent, so now the speed value has to be decreased by an amount of 4/5 speed of the what is calculated for the in the presence of the curve. So that value can be taken as 4/5 of 4.4. The value is reduced to 3.52. Okay. So similarly for narrow gauge, it can be taken as V is equal to 4/5 of the previous formula B, 3.6. So that will gives you 2.92. 3.65 into 4/5, that will comes to the 2.92 value. And the speed restrictions here, the formulas will be valid only up to a speed of 40 kmph. And now for the higher speed, the speed is great. If the speed of the train is greater than 100 kmph, we can use the general formula as V is equal to 4.58 into square root of R, where R in all these formula refers to the radius of curves in meter. So this is how we can determine the speed of the train at the curves. With the condition, what is taking in the view of radius of the curve. So anyways, how to calculate the speed value depending upon the super elevation and the transition curve. So that we will further discuss in the coming sessions. Thank you.